If you're a fan of mystery novels, you know that the clues are often hidden in plain sight. Sometimes the most obvious things can be the most revealing. That's why, as data detectives, we need to pay attention to the details and look for patterns that can help us solve our analytics cases. We'll explore how Microsoft Fabric Lakehouse can help us uncover insights from data using delta tables, a powerful feature that brings relational database capabilities to data lake processing. Welcome, detectives. My name is Jason Richards, Microsoft Technical Trainer and Data Detective. Let's investigate what delta tables are, how they work, and why they're so useful for data analytics. Delta Lake is an open source storage layer that adds relational database semantics to Spark-based data lake processing. Tables in Microsoft Fabric Lakehouses are delta tables, which is signified by the triangular delta icon on tables in the Lakehouse user interface. Delta tables are schema abstractions over data files that are stored in delta format. For each table, the Lakehouse stores a folder containing Parquet data files and a delta log folder in which transaction details are logged in JSON format. What are some of the benefits of delta tables? Glad you asked. With Apache Spark, you can store data in delta tables that support CRUD, or create, read, update, and delete operations. In other words, you can select, insert, update, and delete, for you SQLites out there, rows of data in the same way you would in a relational database system. Relational databases are designed to support transactional data modifications that provide atomicity, which means transactions complete as a single unit of work, consistency, which means transactions leave the database in a consistent state, isolation, which is in-process transactions, they can't interfere with one another, and durability. When a transaction completes, the changes it made are persisted. This spells out ACID. So when I refer to ACID, that's what I mean. Delta Lake brings the same transactional support to Spark by implementing a transaction log and enforcing serializable isolation for concurrent operations. Because all transactions are logged in the transaction log, you can track multiple versions of each table row and even use the time travel feature to retrieve a previous version of a row in a query. Most relational databases include tables that store static data. Spark includes native support for streaming data through the Spark Structured Streaming API. Delta Lake tables can be used as both sinks or destinations and sources for streaming data. The underlying data for delta tables is stored in Parquet format, which is commonly used in data lake ingestion pipelines. Additionally, you can use the SQL Analytics endpoint for the Microsoft Fabric Lakehouse to query delta tables in SQL. Delta tables are a powerful way to store both static and streaming data in a structured format that supports transactional updates, time travel, and schema evolution. Delta tables can be created and queried using Spark SQL or data frames, and they can be stored in either managed or external tables. Let's investigate how to create these Lakehouse-friendly tables and explore the differences between managed and external tables. Ready to dive into the case of Delta Detective? Let's go. When you create a table in Microsoft Fabric Lakehouse, a delta table is defined in the metastore for the Lakehouse, and the data for the table is stored in the underlying Parquet files for the table. One of the easiest ways to create a delta table in Spark is to save a data frame in the delta format. For example, the following PySpark code loads a data frame with data from an existing file and then saves that data frame as a delta table. The code specifies that the table should be saved in delta format with a specified table name. The data for the table is saved in Parquet files, regardless of the formatted source file that you loaded in the data frame, in the table storage area in the Lakehouse, along with a delta log folder containing the transaction logs for the table. The table will be listed under the Tables folder for the Lakehouse in the Lakehouse Explorer. You can also create delta tables by using the Spark SQL Create Table statement, as shown here. This action saves the table similarly as the previous example to the table storage. You can also create a table by specifying an explicit file path. Here, we're creating a parameter called delta path and referring to it in the save function. Because we're writing the table to a file location, this will be saved as an external table. The table name will still appear under the table storage location, and the Parquet data files and the JSON log files for the table are stored in the files storage location, and it will be shown in the files node in the Lakehouse Explorer pane. So what's the big deal between a managed and an external table? Let's solve this mystery. When a table is created, two parts are saved. A table definition, which is the metadata or pointer to a table, as well as the actual data and the associated logs. When creating a managed table, the table definition and the underlying data files are both saved and managed by the Spark runtime for the Fabric Lakehouse. Deleting the table will also delete the table definition and data from the Lakehouse. When creating external tables, the table definition, while still in the metastore, directs or maps to the data which is stored in an alternative file storage location. This means that deleting an external table will remove the table from the metastore, but does not delete the associated data files. This approach can be useful when you want to create a table definition that references data that's already been saved in a Delta format, or based on a folder where you expect to ingest data in Delta format. Certain scenarios may require you to save data in Delta file format as opposed to a Delta table, which essentially prevents a table definition from being created. This approach can be useful when you want to persist the results of data transformations performed in Spark in a file format over which you can later overlay a table definition. It's also good to note that you can still get the benefit of a transaction log that is saved with the file. Then there may be other scenarios where you want to save just a table definition that could be used to populate tables later. You can use Spark code to accomplish this as well. Now that we have Delta tables created, how in the heck do we work with these things? Another case to crack wide open, detectives, so grab your magnifying glasses and let's look for clues. Probably not much of a shocker, but you can work with Delta tables or Delta file formats to retrieve and modify data in multiple ways. The most common way to work with data in Delta tables in Spark is to use Spark SQL. You can embed SQL statements in other languages, like PySpark or Scala, by using the Spark SQL library. For example, the following code inserts a row into the products table. You can also use native SQL statements. You can either use Spark SQL as the default language in a notebook, or use a magic operator that will override the default language in a notebook. Here, we're updating the products table by changing the price of a certain product. When you want to work with Delta files rather than catalog tables, it may be simpler to use the Delta Lake API. You can create an instance of a Delta table from a folder location containing files in Delta format, and then use the API to modify the data in the table. Here, we're defining a Delta table object in memory and updating the prices of all accessories. This will update the file without persisting a table in the Lakehouse. Yes, detectives, time travel is possible, but not in the sense you might be thinking. Modifications like updates made to Delta tables are logged in the transaction log for the table as JSON files. Not this JSON, by the way. Each JSON file serves as a version of the table. Because of this, we can use the log transactions to view the history of changes made to the tables and to retrieve older versions of the data, known as time travel. To see the history of a table, you can use the describe SQL command, as shown here, and the results of this statement show the transactions that have been applied to the table. To see the history of an external table, you can specify the folder location instead of the table name. You can retrieve data from a specific version of the data by reading the Delta file location into a data frame, specifying the version required as a version as of option. Another case solved, but more mysteries abound. All the data we've explored up to this point has been static data in files. However, many data analytics scenarios involve streaming data that must be processed in near real time. For example, you might need to capture readings emitted by Internet of Things or IoT devices and store them in a table as they occur. But where do we store the streaming data? How do we query it? More mysteries. Are you ready, detectives? Let's dive into the clues and see how Fabric can help us handle streaming data with Delta tables. A typical stream processing solution involves constantly reading a stream of data from a source, optionally processing it to select specific fields, aggregate and group values, or otherwise manipulate the data and write the results to a sink. Spark includes native support for streaming data through Spark Structured Streaming, an API that is based on a boundless data frame in which streaming data is captured for processing. A Spark Structured Streaming data frame can read data from many kinds of streaming sources, including network ports, real-time message brokering services like Azure Event Hubs or Kafka, or file systems locations. You can use a Delta table as a source or a sink for Spark Structured Streaming. For example, you could capture a stream of real-time data from an IoT device and write the stream directly to a Delta table as a sink, enabling you to query the table to see the latest stream data. Or you could read a Delta table as a streaming source, enabling you to constantly report new data as it's added to the table. In the following PySpark example, a Delta table is used to store details of internet sales orders. A stream is created using the read stream method that reads data from the table folder as new data is appended. After reading the data from the Delta table into the streaming data frame, you can use the Spark Structured Streaming API to process it. Here, the data frame is simply displayed, but you could use Spark Structured Streaming to aggregate the data over temporal windows, for example, to count the number of orders placed every minute, and send those results to a downstream process for near real-time visualization. Okay, so we're capturing boundless data and performing ETL on it in real time. But what about when we're ready to write the data to a source? No problem, detectives. In the following PySpark example, a stream of data is read from a JSON file in a folder. The JSON data in each file contains the status for an IoT device, so the fields that we're collecting from the JSON file would be device and status. New data is added to the stream whenever a file is added to the folder. The input stream is a boundless data frame, which is then written in Delta format using the write stream method to a folder location for a Delta table. You may also notice the checkpoint path indicated in the code. The checkpoint location option is used to write a checkpoint file that tracks the state of the stream processing. This file enables you to recover from failure at the point where the last streaming process left off. After the streaming process is started, you can query the Delta Lake table to which the streaming output is being written to see the latest data. Another note, streaming data is boundless, so when a structured streaming job is submitted, it won't stop unless you programmatically stop it. Keep that in consideration when executing notebooks or scripts that contain streaming functions. Now that we've gathered clues on how to work with Delta tables in Fabric, let's connect the dots and put knowledge to practice. We're jumping back into the DetectoLab 5000, aka my Surface laptop, for a go. The game is afoot.
All right, welcome back into the environment. And we're going to cover Delta tables. So up to this point, we're kind of working a little backwards just because this is the way that the content fell in the whole scheme of things, but we want to cover it. So we're going to talk about the Delta tables, and I'll give you a little background for what we've done up to this point, which moved a little bit ahead, and then we're moving back. But what we've done up to this point is we've created a sample lakehouse. We've shortcutted into that. And then what we did was we loaded data into our files path into our lakehouse. So if I go into my lakehouse here, you see I have this WWI raw data. And this was actually data that we imported in using a pipeline from an external blob storage account into our lakehouse itself. So when you get into pipelines, this will make a lot more sense. But ultimately, what we have here is a bunch of raw data in Parquet format, right? So I got different Parquet files in here. And usually that's the optimal way of reading data into anything, into the Spark engine. Parquet is very good, is a very ideal file type to work with the Spark engine. And that's why all these are in Parquet. So it's always a good thing to do in the ETL process, especially if we're going to work in Fabric, is to convert your files. If we're going to copy them into a lakehouse or into our OneLake, we want to go ahead and convert those through a downstream process to turn them into Parquet files so that if we're going to use a Spark engine, we know it's going to be optimized to work with that file type. They're already there like that. So what we're going to do is we're going to go back into our workspace and open up this notebook. Now, if I would have opened up the notebook, by the way, I'm going to stop this session. And I'm going to make sure that I have my lakehouse enabled on this, right? So you can see that my Explorer, I could upload data and files to certain resources, but also if I want it to load it up to a lakehouse, I need to make sure that I have that in there, right? So my lakehouses, I already have one, so we can add those to it. But I want to make sure that this item's added, because I'm going to be referencing file paths in there, and I want to make sure that the lakehouse is the file path that it's looking for in the session. So we're going to run this cell, and the first thing I want to talk about while we're running this cell, and we'll go through this again, is these configuration settings. Now, we are working with Spark Engine in this case, and if we're going to be utilizing our SQL Analytics endpoint or using downstream analytics tools like Power BI, this optimization open source project called vOrder allows the data that we're going to load into these tables to be compressed and optimized for reads from those downstream resources that I just mentioned. Also, this optimize write is a good optimization technique to include whenever we're writing tables to a Delta format. So they do have to be Parquet format in order for you to utilize things like vOrder. But we also want to optimize the writes in these Delta table formats so that we're maximizing read times when it comes to querying these particular tables. So that's what I'm doing in here. I'm enabling vOrder or making sure it's enabled. This way I got all my bases covered. Same thing with optimize writes. I'm making it enabled. And then I'm also setting a bin size, which means that it's going to try to write these to a certain size file, and then whatever's left over, it'll make its own folder for that amount. So this is a bit size or a size for that. So the first thing that we're going to do is we're going to create a fact table out of those files that we loaded into our lakehouse. So what do I need to do? Just to go over the Python here, I'm importing some SQL functions, because what I'm going to do is I'm going to be parsing out certain values contained within columns and making our own columns out of those values, so to speak. So what I'm doing here is I'm setting a variable name called fact sale, and we're going to apply this to the table name. That's a string value. And why? Because we're going to insert it here later on. This seems like a little overkill because I could have just entered fact sale there, but if we had multiple tables that we were creating, I could see why you'd want to do this. Now, going back to Python, in order to create a Spark data frame, we talked about Pandas data frame, but in order to create a Spark data frame, just utilizing the Spark commands, I can go to the Spark and then do a read. So this is what loads data into a data frame. I'm making a data frame API call out and setting it to the designation or variable df. I'm telling it that the files are going to be in Parquet format, and where to look for those files. So there should be a files path for my raw data, a full, and then a fact sales year 1. Just as a sanity check, I can look full, fact sale, 1 year full. So I know it's in here, right? Very good. Know it's there. And what we're doing here, after we read the data in, it should create that data frame. And now I'm going to overwrite this data frame since it's the same variable, but I'm including these column values. So now I'm creating a column called year, where I'm pulling out the year from a date time column, and I should be able to parse out certain aspects of information from that. Also, I'm going to pull out the quarter of that and create its own column, and same thing with the month. And then I'm going to write this. So when I use a Spark write command, I'm externalizing this data. It's all held in memory until I externalize it. So this Spark write method allows me to essentially write this to an external place. Now we're going to be writing it to our lakehouse, right? In the tables, that's what I'm identifying here. We're also going to be converting it to Delta Parquet format, and we're going to partition them by year and quarter. So there'll be folders made for both all the years in the data set and then all the quarters in the data set as well, following those optimization techniques. So this might take a little bit of time because it's going to read all this data in. If it's a full year's worth of data, it may be several megabytes worth of data. And then it's got to apply these transformations to it. And then it's going to write it to the Delta Parquet format file. And this is what's going to essentially create our Delta tables in our lakehouse. This is really all I'm doing. This right here is what's converting this or creating Delta tables. I'm just saving it under the table's name and then writing them to this. So I'm going to let the magic of editing, video editing, come back when this is done. All right, so it looks like the cell executed. Welcome back, by the way. Fast forward in time. We are time traveling ourselves. So now we've actually created a table. So let's do a sanity check, right? I want to see if this happened. So we'll go back in our lakehouse, and there it is. There's our fact sale table. Now I'm in my file explorer right here, so I can see my data that's open, that's created from this. And then I could always go into the fact and the Parquet files in here. But I can also view the files. So this is what I wanted to point out for this, because this is what essentially has created this Delta log here, right? Or this Delta table and what it includes. So you see here that I have a Delta log, right? And then I have this year folder. Let's go back because I want to show, first I want to show let's go back to the files. So the Delta log is my transaction log, right? If I go in here, there should only be one version of this because I just created this table. So you can see there's a bunch of spaces in there. If I were to update this table with some different information, even if I was to change a column name, filter some data out, do something of that nature, it's essentially going to update this table just like it would in like SQL if we were doing this there. Difference is that it's a JSON file and we associate it directly with the other files that are in this path. So what it'll do is it'll call on the metadata associated with a specific version. I don't know if I can open these or not. So yeah, I can. So you can see that there's info associated with this, right? And it just has everything that I've done up to this point. So this is all metadata associated with all the files. Go back in here. So this is the metadata associated with all the files that were in the path that I created. So this is our transaction log. I update it. This is what allows me to do time travel and go to different versions of the log. Now, about the partitioning. Remember, we used a partition by strategy. So we can partition our data out using that strategy. I'll go back and show you, but Remember, we did it by year and by quarter. So it created a year because there was only 1 year in the entire data set. If it had more than year 2000 in there, it would have created another folder for year 2001. But it only has 1 year in here, right? That's what we pulled it from, was this fact sale 1 full year. So it should only have 1. And in that year, it has 4 quarters. So it also can split this data by quarter. And then you can see that it created a partition file for each one. Or I keep doing that. I want to navigate through that way. So you can see that each one of these is about, 58, 59 megs. So this is kind of what that optimization does too. And then it created a final file that was around 39 megabytes. So this is essentially what the optimization does, what happens when we write this and when we partition it by using a Parquet file in these deltas. So the delta applies the transaction log. The Parquet partitions the files for super fast read times on this. So now I can essentially go back in here and directly query this data. And we'll come back and do that here in a second. But let's go back into this, because I don't just want my fact tables. I want dimension tables, right? I want to start building a model from this data. So this is what this particular cell does. And I'll go through this too, because we're doing this a little bit differently. And usually you'll see this when we talk about Spark execution jobs, or you hear about Python scripts. This is a notebook, but you can create Python scripts. And usually the difference between what would happen in a script and this is that we're not really including all this markdown language in there. We're going to refactor the code to define functions as opposed to calling functions out in line by line. We're going to define a function and then execute the function in some type of order, execute the collection of functions. So in this case, this is a good first step. I would say this is 80% of what a Python script would look like, except that we would include, some executables for the we would define a main run and then execute the main run. Here, we're just running a for loop to execute the actual function itself. So what are we doing here? Let's get to the point, Jason. All right, so we're defining a function called low-fold data from source. So I'm creating this. And the argument that it is going to require is a table name, right? So what is this function going to do for me? So when this gets called out, it's going to read data in from my files and then pull in a table name that I'm defining, right? So, and I'll infer that later on down here. So this is why I'm creating these table name, this table name variable right here. So this is what it's calling out, which I would name here. Then I'm selecting columns. If C is not equal to photo, so I'm going to include every column except for this photo column, which I'm assuming contains an image that we just don't want to include in this. And then we're going to write these to a delta table. So this is just another way of doing this. I can create, essentially define functions, write this as script, Python script, save it as Python script, refactor it like I am here, and then run it as a Spark execution job on a schedule. So then I could constantly check for data in my lakehouse, pull it in from there, and update the tables that are contained within my within the lakehouse itself as well. Now, what I'm doing here is I'm defining a list of tables that I want to pull out, right? So this is what it's doing, is now it's going, when I execute this, and this is a for loop, so it's going to keep going until it's iterated through this list of items here. So it's going to look for dimension city, dimension date, dimension employee, and dimension stock item. And then it's going to run this function on them, right? For each table that's listed in this list. So hopefully my Spark session didn't end and we'll be able to pull this in. We're still associated in our file explorer with our lakehouse. So that's where it's looking for these file location names at. And I got to tell you, that was super quick in its way of, now these are just dimension tables, so they're probably super small tables. But let's go back into our lakehouse and take a look. So you can see it's already refreshing. And again, now I have my dimension table. So I have my dimension city, my dimension customer. I can click on this. It'll load a preview of the table for me, right? So, and this is, 402 rows in this one. This only shows a max of 1,000, so there's probably more than that in there. My dimension date probably has way more than 1,000 rows in it. Dimension employee, maybe not so much, 213 rows. Right. And then dimension stock items, we have 672 stock items in here. So customers and dates, probably more than 1,000. Some of these are cities, I'm sorry. So our cities, there's more than 1,000 cities and there's more than 1,000 dates. But this is essentially what created all of our Delta tables. And each one of these, view the files, it's going to have a Delta log and it's going to have its own file associated with that. It didn't partition or it didn't create folders. Why? I didn't use a partition by statement in the actual loading of the table, right? I don't have a partition by here in the right as I did up here. Boom. This had a partition by. And dimension tables are usually small enough where you shouldn't have to partition them by anything. Fact tables, you'll usually want to use like a partition or a date that's going to split the data as evenly as possible. They probably did this twice to further split that data to be more optimized on the read part of it. And sometimes you'll have to do that. But that pretty much introduces the concept of Delta tables. Let's go back into the studio.
Yes, fellow detectives, this is how we Delta in Fabric. Delta tables are a key component of the Lakehouse architecture, providing transactional support, schema evolution, and time travel capabilities. They also integrate seamlessly with the Fabric Lakehouse user interface and the SQL Analytics endpoint, making them easy to explore and query. Whether you're investigating static or streaming data mysteries, Delta can help crack the case. Thanks for joining.